Alright, I promised you with a build up to things, so let's get things started. Let's light the lights and let's make the final step happen for ionic equations tonight. What is an ionic equation? And what does it have to do with our precipitation reactions? Ionic equations display how things actually exist. Rather than write them in a way that's nice and neat, ionic equations display how the compounds, atoms, and ions exist in reality. The big thing is an ionic equation displays soluble ionic compounds and strong acids as ions. In an ionic equation, soluble ionic compounds and strong acids will be written as ions. I capitalize strong acids for a reason, and soluble should be capitalized as well, because if it's not a soluble ionic compound or a strong acid, then we're going to write the compounds the way they normally would. How we normally write equations, how we're used to seeing equations, that actually has a name to it. Those are referred to as molecular equations. A molecular equation is how we normally write things, and all compounds are written as compounds. Let's take a look at the molecular equation for the reaction of silver nitrate and potassium chloride. This is the molecular equation. When we write the ionic equation, we're going to split apart any ionic compound that's aqueous. Remember when we talked about electrolytes, we said that ionic compounds split up into ions when they're in water. So if we were to look inside a glass of water, we wouldn't really see silver nitrate, right? What we'd actually see, we would see the silver ion floating around, and we would see the nitrate ion floating around, because in an ionic compound that's soluble in water breaks up into its ions. Same for our potassium chloride. We wouldn't see potassium chloride together as a unit if it's dissolved in water. Instead, and this little squibble here is AQ, right, in parentheses, what we'd see instead we would see the chloride ion and the nitrate ion. We'd see the potassium ion and the chloride ion separated. Let me clean things up here a little bit for you. So that's what we'd actually have on the reactant side. Physically, if we looked inside our water, we'd have a bunch of silver ions floating around, a bunch of nitrate ions floating around, a bunch of potassium ions floating around, and a bunch of chloride ions floating around. Not these units together. On the product side, however, silver and chloride have found true love, right? They've formed a precipitate. They are more attracted to each other than they are to water molecules. So they're going to come out of solution, and because they come out of solution and they formed a solid, they actually exist as a solid. They actually exist as a unit of silver and chloride. So when I'm writing this ionic compound that shows how things physically exist, I'm going to keep them together as a unit. My potassium nitrate, however, that's not the case, right? Potassium nitrate are aqueous. And we know from our electrolyte lecture, if it's aqueous, it's broken up. If it's aqueous and ionic, it breaks up. So our potassium and our nitrate ions would be written separately. What I have written for you right here, this long drawn out thing, is known as an ionic equation. couple important things to keep in mind. When we're dealing with ionic equations, phases are important because phases determine whether or not something's broken up or together. I will take off points if phases are absent or they're wrong. Right? I went to all the effort to make my little AQ squibble there in parentheses next to everything. If phases are missing, your equation is wrong. The other thing is, it's an ionic equation. Don't forget to write your charges. If your charges are missing on your ions, then the equation's wrong, right? I can't just write silver. I have to write silver plus 1. I can't write just potassium. I have to write potassium plus 1. I can't just write chlorine. I have to write chlorine negative 1. Who shouldn't have charges showing? My compounds together here, right? So it doesn't have any charges showing. You have to be careful. These are the sorts of questions where I always recommend that you double or triple check your answers on exams. Because it's really easy just out of sheer absent-mindedness to forget a phase or to forget a charge. Writing an ionic equation is really pretty easy. All you're going to do is you're going to break your ionic compounds up into their ions, and then you're going to balance. The place where people run into problems with ionic equations is they want to invent ions. Remember your nomenclature rules. If you can't name it, you can't write it. For example, let's take a look at this equation here, where we have strontium chloride, aqueous, reacting with potassium sulfate, aqueous. Our first step is to break our aqueous ionic compounds up. I have strontium chloride right here. Strontium's a group 2A element, so I know it's going to be 2+. Then I have chloride. Have you ever memorized a Cl sub 2 ion? No. So don't invent one. It's a plus sign right there. So your ion is going to be chloride, group 7A, so it's -1. Then we come to potassium sulfate. Potassium is group 1A. Again, have we ever memorized something K sub 2? No, so don't invent a polyatomic ion when you haven't memorized one. So that's potassium plus 1. Then you should have memorized and should recognize that SO4 is sulfate. Now the other side of the arrow here, I wrote way too large. Hard not to do, quite frankly, with the stylus. We have strontium sulfate solid. If it's a solid, that means that the attraction the ions have for each other is greater than our attraction for water. They love each other, and no water molecule in the world can pull them apart. So they're a solid and they stay together because they physically exist together. Potassium and chloride, however, they have no love for each other. So they're broken up. They've broken up. Just did something weird. And I meant that on the computer there. All right. Potassium, and then it's chloride, so it's -1. Now balance. I have 1 strontium, 1 strontium. I have 2 chlorines up here, so I'm going to have 2 chlorides in my equation. I have 2 potassiums, so I'm going to have 2 potassiums in my equation down here. Right? I'm taking care of those subscripts now with a balancing step, not by inventing new ions. 1 sulfate, 1 sulfate, 1 strontium, 1 strontium. I have 2 potassiums over here and 2 chlorides over here, so I have to add 2 potassiums here and 2 chlorides there. And that's it. As long as you remember your nomenclature rules, writing ionic equations is easy. They're so easy, in fact, that Kermit could handle them with no problem. He would find them much easier than being green. Everybody write down Kermit. K-E-R-M-I-T. Kermit. After you write down Kermit, I would strongly urge you to pause the reaction, pause the lecture, and try this on your own here. Apparently I need lunch. Pause the reaction and try this on your own. Did you pause me? Please tell me you paused me. I know I've been going on for a while now, but I really want you guys to try this on your own. Look me in the eye. That's right. Screen to eyeball here and tell me that you paused this. All right, let's check. First step, break things up that are aqueous. So I've got lead 2 nitrate. So I have lead 2. I know it's lead 2 because of my nomenclature rules. Right? I've memorized that I have nitrate at -1. And I know I have 2 of them. So my lead would have to be, well, 3s are just impossible to write with a stylus. All right, there we go. Then I've got potassium again. And I've got bromide. Now on the product side, lead 2 bromide's a solid, so it stays together. Solids stay together. Remember, they've found true love. They're not going to be torn apart by the water molecule. And we've got our potassium. And I'm just out of room. And our nitrate. Now we balance. I've got 1 lead, but I have 2 nitrates, so I'm going to have to add 2 nitrates here, 2 potassiums, 2 bromides, 2 potassiums, 2 nitrates, and now I have to say it, chemistry's easy, life is hard. Let's take a closer look at this reaction. Okay, same reaction right here. The reaction we just solved for. And here's our ionic equation, right? If you couldn't read my chicken scratch, here it is, nice, neat, and typed out. Didn't know I could do that, huh? if you look at this reaction, there's something that leaps out at you. Why does it leap out at you? Because I put it in a different color than the others. You'll see that you have both potassium and nitrate occurring on both sides of the equation in the exact same fashion, right? I have 2 potassium ions here, and I have 2 potassium ions here. No change. I have 2 nitrate ions here, and 2 nitrate ions here. Again, no change. So if they're not changing, are they really participating in the reaction? No, they're not. They're what are known as spectator ions. Ions that do not participate in the reaction. They are just present on both sides of the equation, and usually they're just used to get the other ions into solution. So my potassium and nitrate aren't participating in the reaction. That makes them spectator ions. So my potassium and my nitrate are spectator ions. So we can cancel them out. They appear on both sides of my equation, so I can go ahead and cancel them out. That leaves me with just the ions that are participating in the reaction. My reaction is really a love story between my lead and my bromide getting together. My lead 2 ion reacts with 2 bromide ions to form lead 2 bromide solid. That's the actual reaction occurring. We refer to what I've written here as the net ionic equation. The net ionic equation displays only the ions that participate in the reaction. Now, every chemistry textbook you read in the entire world will tell you that the way that you get the net ionic equation is to write the ionic equation and then cross out anything that appears on both sides. And that is the pinky way out. That's the pinky finger out way of doing it. It's also the hard way and the way prone to give you mistakes. Here's the easy way to do it. And here's the way I did it as an undergraduate, and I would recommend that you address it. Identify your precipitate. In this reaction, our precipitates are lead 2 bromide. The precipitate's always going to be the product of your net ionic equation. To get the reactants, just split up your product. To get the reactants in your net ionic equation, just split up your product. I've got lead 2 here, so that's going to be 1. Then I've got bromide there. Don't forget phases. And then balance. That's the easy way to do it, right? Identify that precipitate and then break it up. Chemistry is easy, life is hard. Although life could be very hard if you're dealing with Miss Piggy on a daily basis. Write down Miss Piggy. M-I-S-S and then Piggy. P-I-G-G-Y. Piggy. All right. Write the net ionic equation. Identify the precipitate, then write the ions that make up the precipitate on both sides. So we've got an equation here, and we're being asked to write the net ionic equation. Rather than write the full-fledged ionic equation, since they're just wanting the net ionic equation, I'm going to identify my precipitate, my solid, calcium sulfide. And then I'm going to write the ions that make it up on the reactant side. So I have calcium, and calcium is going to be a +2. And remember, it's on the aqueous phase. And then it's reacting with sulfide, 2 negative, also in the aqueous phase. Balance, well, 1, 1, 1, 1. So I'm balanced. Chemistry is easy, life is hard. Let's have you try one. All right. Pause me, try it real quickly. Did you pause me? I paused. I paused. Did you pause? Do you have a pause connection? All right. Ooh, we sound like dogs. We got pause here. Ooh, now I'm thinking Planet of the Apes. Keep your stinking paws off me. Ooh, all right. Now I'm really thinking Planet of the Apes. All right. Identify your precipitate. think I'm going to watch that tonight. The Charlton Heston version, not the Mark Wahlberg version. Oh, whoops. Identify precipitate. Too distracted. My precipitate's always my solid. So I've got magnesium sulfide. Write the ions that make it up. Magnesium and sulfide. Chemistry is easy, life is hard. Here's what we've been building to the entire time. I'm giving you two reactants. I want you to complete the molecular equation. In other words, I'm wanting you to tell me what two products are going to form. Then write the ionic equation. Identify the precipitate. Identify the spectator ions. And write the net ionic equation for me. That's 4 things. Deep breath. We've spent the last couple hours doing each one of these 4 things as a separate problem. So all I'm asking you to do is what you've already done. First thing I would do is I'd complete that molecular equation. Completing that molecular equation also gets us a step towards the ionic equation. Because what's the first thing we do? Oh, and pause me, by the way, and try this on yourself. The first thing we do when we're writing that molecular equation is we list the ions, right? I've got silver. I've got perchlorate. I've got sodium. And I've got iodide. Well, remember, outside, inside to form my new compounds. So my silver and my iodine are going to form a new compound. And my sodium and my perchlorate are going to form a new compound. Now I need to assign phases. So I've got silver iodide, and I've got sodium chlorate. My phases. Do I have a rule that involves sodium? Yes, anything with a group 1A element is soluble, so it's aqueous. Anything that contains iodine is aqueous except for silver. Silver is an exception. So it's going to be a solid. Now we balance, and we're balanced. Everything's a 1-to-1 ratio. This is my solid, so it's my precipitate. What about my spectator ions? Easy way to identify spectator ions. They're always going to be the ions that make up the aqueous product. And here our aqueous product is our sodium chlorate. So the ions that make up our sodium perchlorate are sodium and perchlorate. So they would be my spectator ions. Whatever the ions are that are in our aqueous product are always going to be our spectator ions. So it's sodium and perchlorate. Remember, they have to be ionics. Our ionic equation, we're almost there, right? We already listed our ions up here. We just have to do the products. Silver iodide is going to stay together because it's a solid. Sodium perchlorate's aqueous, so we split it up. So there's our ionic equation. Now for our net ionic equation, we simply take our product, that's our precipitate, silver iodide, and we split it up into the ions that make it up. And we balance, and we're balanced. Booyah! What can I tell you? Chemistry is easy, life is hard. Also, as a parting gift, why don't you write down beaker? Write down beaker. Meep, meep. Write down beaker. If you've written down beaker, you're free to go. Why are you still listening? Bye. Ooh, why are you still here? Have you seen the teaser scene in Deadpool? That is actually a teaser scene to Ferris Bueller's Day Off.